I like to talk about valence electrons again first, just to review, because to me, valence electrons are what makes the periodic table so interesting and why it has all the properties that it does. It's all based on the valence electrons. It always comes back to that. So remember that the valence electrons are the outermost electrons, and we sometimes draw these electron dot diagrams to depict how many valence electrons each atom has. And if we go across the second period, from lithium all the way over to neon, and look at their electron configurations, we can see that the second energy level is going to be the valence energy level for all of these atoms, and that as we go across, each one gets one more valence electron. Lithium starts off with 1, and beryllium then has got 2. Boron has got 3. And as you draw these diagrams, remember that it's important that you just go across. It doesn't matter which side you start on, but you always want to cross as you go. And each side should get 1 electron before any side gets 2. It's a little bit like filling out an energy diagram that way. The nitrogen rather is going to have the 4th one go on the bottom, and then it's going to start again on the right side. And so as we go across here, we have oxygen with 6, fluorine with 7, and neon has got all 8. It's the noble gas in that family. Now, that leads us to a pattern where we can see that anybody in that first column is going to have 1 valence electron. Anybody in the second column is going to have 2. That middle group right there technically has got 2, but I don't want to say that for sure. We have to work on it. Let's just not have a rule about that. The next column, boron's family, those guys will all have 3 valence electron. Carbon's family has got 4 valence electrons. Nitrogen's is 5. Oxygen's is 6. Fluorine, the halogens, have got 7 valence electrons. And the noble gases have 8, except for helium, which only has 2. Now, what we're going to talk about today really is the trends in the periodic table, and there's 3 that are very popular in chemistry textbooks and on tests. 3 that we're going to teach you about that I want you to know. The first is atomic radius. That's how big is the atom, the radius from the nucleus out to the furthest electron. The next one is first ionization energy. That is, how much energy does it take to steal 1 electron away from an atom, to take 1 of its electrons. And the last one is electronegativity, which is how hard does an atom pull on his neighbor's electrons. So let's take a look at atomic radius. And the first pattern we're going to look at atomic radius is how the atoms change in size as we go down in a family. So we'll look at hydrogen to start with. Hydrogen's got 1 proton and 1 electron, and that's going to be in the 1s energy level. And so we will just depict it like this, with a positive in the middle and a negative going around the outside. We're going to use the Bohr model of the atom for this discussion, and we know that the Bohr model of the atom isn't correct, but that doesn't mean that it's a bad model to use. If it gives you the prediction that you need, and if it's useful for explaining something, then let's use it. So we're going to use the Bohr model of the atom here, with the electrons going around in circles. As we go down from hydrogen to lithium, we've got now 3 electrons and 3 protons in the middle, but you can see we've started to fill the second energy level because we filled up the 1s's and now we're on to the 2s's. So we've got a bigger atom here because we've got another layer of electrons. And as we go down the next step to sodium, we see that the same thing happens again. We've filled up the 2s and the 2p underneath. We've moved on now to the 3s, and we've got 11 electrons along with 11 protons. So it's a little bit like an onion. As we go down from one atom to the next, we're adding another layer of electrons. As we go to potassium here, we start the 4th energy level, and that electron is going to be the furthest one away, and so the atom is getting bigger. So the family trend for atomic radius is that the atoms get bigger as you go down. Let's back up to sodium before we talk about the period trend. As we go across the table from sodium, we've got 11 protons and 11 electrons. All right. As we go across now, if we go to the next element is magnesium right next door. Magnesium has added 1 more electron. It's right there. But in addition to 1 more electron, it has also added 1 more proton. Now, the electrons is in the same energy level as that first electron was in the 3s, and so it's not really any further away. This electron isn't really any farther away than that electron, so the atom didn't get really much bigger. In fact, the extra positive charge in the nucleus, actually the positives and negatives are attracting, and so the extra positive in the nucleus pulls those energy levels in a little bit. If we go to aluminum, we add the 3rd electron in that energy level, but we also add another proton. And so we have got electrons going the same distance away from the nucleus because we're still filling that third energy level, but the nucleus is getting more positive, and so what we're having happen here is that these energy levels are being sort of sucked inward. When we fill the fourth electron in that energy level, we have to add another proton down in there as we go across, and these atoms are getting smaller and smaller. Eventually, when we get to phosphorus, we have added the fifth electron, and we continue to add protons into the middle, and so we are going to have a smaller and more dense atom. Now, so if we back up here, you'll see this atom grow as we go back. So the elements get smaller, the atoms get smaller as we go across. Now, this is kind of counterintuitive. People would like to think that they actually get bigger because their atomic number is getting bigger, and it is. But the element itself, the atom, is getting smaller because of this drawing in of the energy levels. So for atomic radius, the period trend is decreasing. As we go across the period from left to right, the atom's size decreases, and the family trend is increasing because as we go down, we're layering more and more electrons on, kind of like an onion. This is a little picture here that kind of is a picture of that. Each of the circles, each of the little balls, the size represents the size of the atom, and you can see that the cesium atom, way down in the bottom left corner, is the largest of all the atoms, and helium up in the upper right is a very small atom. Now, before we can talk about ionization energy and electronegativity, we need to take a second and talk about what ions are in the first place. And this is going to take a little bit, but it's an important step. All atoms are trying to get an electron configuration like a noble gas. Having 8 valence electrons is extremely stable. And so we like to say, and oftentimes we'll say that atoms want 8 valence electrons. And it's a tricky thing to say. Atoms don't want anything. Atoms aren't alive. And so when you say that something that's inanimate wants something, you're really kind of making an analogy, and it's maybe not accurate. So what's actually happening there is that it's the most stable situation for an electron, or for an atom to have 8 valence electrons, like a noble gas. Now, there's 2 exceptions. Hydrogen and helium don't want to have 8. They are more stable when they fill up the 1s level. They can only get 2 in there. And once they have those 2, they're done. So they follow the duet rule. Now, atoms will gain or lose electrons to try to end up with 8 valence electrons. And when they do that, that means that they've gained or lost a neutral charge. And so when atoms gain electrons, they're gaining negatives. So that means they're going to end up as a negatively charged atom. If they lose electrons, they're now going to have more protons than electrons, and that's going to give them a positive charge. We call atoms with a charge ions, and what we're going to talk about here is how ions are formed and what sorts of charges they get. Let's take oxygen as our first example. This is oxygen, and that's its electron configuration, 2s2, 2p4. It's got 6 valence electrons. So oxygen looks around at the noble gases that are nearby it and is trying to find out, who would be a good role model for it to try and aspire to be like. And it looks around and it thinks helium and neon. Helium is the noble gas that's smaller than oxygen, and neon is the first one that's bigger than oxygen. So as you look at these, which electron configuration is closest to that of oxygen? If oxygen's going to try to get a configuration like noble gas, which one would be the easiest one for it to copy, to mimic? And you can see that it would have to be neon, because oxygen is going to have to lose all of its two electrons, its second energy level electrons. It's going to have to lose all 4 in the 2p's and 2 in the s's in order to become like helium. But it's only going to have to find 2 more to fill up the p's in order to become like neon. So that's what it does. Oxygen is going to, it's easier to find 2 than it is to lose 6. So oxygen is just going to steal 2 electrons from whoever he bumps into, and it's going to go from being an oxygen atom into being an oxygen ion. In chemistry, when we write charges on things, we write them kind of like exponents. They're kind of up in the upper right-hand corner, and that 2 minus means that it's got a negative 2 charge. That atom has gained 2 extra electrons, so now it's got 8 valence electrons, and it's got a very stable arrangement like a noble gas. But because it gained 2 electrons, now it's negative 2 charge. Let's try another one. Sodium. Sodium's electron configuration looks like that, and the closest noble gases to sodium are argon and neon. Now, if you look, which one is the closest, which one is going to be the easiest one for sodium to change its electron configuration to look like? and it'd have to be neon. If sodium loses one electron, it would be exactly the same electron structure as neon. It would have 8 valence electrons, and that's very stable. It's basically cleaned out its third energy level and gone down to a full 2 level. Argon, it would have to gain 7. So it's very easy to lose 1, but it's going to be hard to find someone 7 to steal. So sodium atoms change into +1 sodium ions. They lose an electron, and by losing an electron now, their nucleus hasn't changed. They still have 11 protons, but they're only going to have 10 electrons now, so they overall have a +1 charge. If the charge is ever +1 or -1, we usually don't write the 1. I mean, you can, it's not a big deal, but usually it's just, we'll just put a plus sign there like we see here, or a minus sign if it's -1. Now, this gives us a good pattern. Just like, and because it's based on the valence electrons, it follows the same sort of pattern as the valence electrons. Since all of the atoms in the first family, hydrogen's family, have got 1 valence electron, it will be easier for them to lose that 1 than it will be for them to try to find 7 to steal. So all of the atoms in that first family will lose 1 electron when they become ions. All of them will form +1 charged ions. And in the second family, we've got a situation where they've got 2 valence electrons. They can either find 6 to steal so they can have 8 valence electrons, or they can clean out those outside 2 and go back to having a full level underneath them, and that's easier to do, so they'll lose 2 and form +2 charged ions. We'll skip over the middle part here, and I want you to be careful. This gray area that I have covered up are ones that I want you to always look on your periodic table for the charge, and I'll teach you how to do that when that's something that you need to know how to do, but for right now, let's just say that they don't follow these rules necessarily. Boron and aluminum are going to lose their 3 valence electrons because that's easier than finding 5 to make 8. They will lose their 3 valence electrons and form +3 ions. And then we get to the middle here. This is kind of like the watershed. This is the top of the mountain. Carbon and silicon have got 4 valence electrons. It's going to be difficult for them either way to get 8 valence electrons, whether they pick up 4 more or whether they lose their 4 and clean out that level and go back to having 4, the full level underneath. So because it's so much work, they don't generally form ions very easily, but when they do, they could go either way. So we could have +4 or -4. Now we're on the other side of the mountain here, because now we've got more than 4. Nitrogen's got 5 valence electrons. With 5, you can find 3. If you can rob 3, then you'll have 8, and so that's what they do. Nitrogen and phosphorus form -3 ions because they go around looking for 3 electrons to steal, and when they do, they have a -3 charge. It's either that or they have to lose their 5 valence electrons, and it's easier to find 3 than it is to lose 5. Oxygen and sulfur are going to pick up 2 more since they have 6 and make a -2 charged ion. And the halogens, they've got 7 valence electrons. They're going around and they are very reactive because they will mug anybody to take 1 electron away so that they can have their 8th valence electron. They form -1 charged ions by picking up that 1 more electron. And the noble gases, this shouldn't surprise you, don't form ions at all. Why would a noble gas want to lose or gain electrons? They've already got 8 valence electrons. That's a very stable situation. They hold on to those electrons very tightly. Okay, so when we talk about first ionization energy now, the pattern, what we're asking here is how hard is it to take an electron away from one of these atoms? And now think about what we just learned. The first column forms +1 ions. They actually want to lose that electron. If they lose that electron, then they emptied out the energy level, their outside one, and they go back to having a full level underneath. So in the first column, hydrogen's family, it's very easy to take electrons. But as we go across, if you try and take an electron away from a halogen who's got 7, they've been saving up their whole life to get the 8th valence electron, and now you want to take one away from them, you have to fight them pretty hard in order to get an electron from them. So the family trend, or rather the period trend for first ionization energy is that it's easy to take electrons away from ones on the left, and it gets harder as we go across to the right. So the noble gases, you have to get into a death match with a noble gas in order to take an electron away from it. It's extremely hard to take electrons away from noble gases, so that's very difficult. As we go across, it gets more and more difficult to take electrons away. It's easy to take them away from the ones on the left. And then as we go down, I like to think of it this way. I mean, if you go from hydrogen to lithium to sodium down that first column, the reason it gets easier to take electrons away is because we have more and more and more electrons. If we get way down to the bottom there by francium, 87 electrons total, not just valence electrons, but all of the electrons. it's easy to sneak one away from there, to steal one, because there's so many. But when you only have a few, you're going to hold on to those electrons a little bit more closely, or watch them a little more closely. That's a kind of a personification of an atom, but that's an easy way to remember it. And the last period, or the last trend we want to talk about is electronegativity. And this is kind of like, I like to say, what is it? I think it's the 8th commandment, thou shalt not covet your neighbor's property. Electronegativity is kind of like, how much does an atom covet his neighbor's electrons? How hard does it pull on his neighbor's electrons and want to gather them towards himself? And so think about it for a second. Which atoms are going to want to take their neighbor's electrons the most? And if you're thinking about it right, you're thinking about like halogens, the ones with 7 valence electrons. They want one more electron, and they'll steal it from anybody. So as we go across the period to the right, we increase electronegativity. The atoms become more covetous. And then as we go down, the atoms have got more and more total electrons, not just valence electrons. And so we lose electronegativity because as they have more, they have less pull on the other ones around them. Here's a periodic table that's been colored in with the darker blue color, meaning more electronegative, more covetous of his neighbor's electrons. And you can see that fluorine is the most electronegative of all the atoms. It tries to steal atoms the most, or steal electrons the most. It's the biggest electron klepto of the entire periodic table. And up in that upper right-hand corner by fluorine are other ones that are also quite electronegative. And as we go across to the left, they become less electronegative. And as we go down, they become less electronegative. And so those are the 3 trends that you should probably know for any sort of chemistry test, including mine, about on the periodic table. They get asked about a lot. Is that atomic radius, first ionization energy, and electronegativity. And now you know a little bit about why those patterns exist the way that they do.